VLSos here. This is a video lesson on piecewise functions. A piecewise function is a single function that is defined to have pieces or different expressions, different mathematical expressions for different places in the domain. What it looks like is defining a function f of x is equal to distinct pieces, in this case a quadratic piece and a linear piece, tied together with a bracket to suggest that these two pieces are taken together as a single function. And we can have as many pieces as we wish. This example will be a piecewise function with two pieces. But it's not the entire graph of this quadratic and this line. For it to be a function, these two expressions can't overlap, which means that another part of the definition is that we have to express the domain for which we use the different pieces. So this will be the quadratic piece, x squared plus 2, for values of x that are less than or equal to 2. And it will be this linear piece, 1/2 x plus 1, for values of x in the domain that are greater than 2. This function is defined for all x. You can put any x value into this function, but depending on what x value you put in, you're going to use a different piece, but never two different pieces for the same x value. So what does the graph look like? I can see that 2 is a special value for x because it's where the pieces are going to change. So I'm going to highlight where 2 is on my axis, x-axis. And my strategy for graphing piecewise functions is to first consider what the entire graph of each piece is, and then at the end clean it up so that it remains a function. So the first thing I'm going to do is I'm going to think of the graph of x squared plus 2. It is the parent parabola moved up 2. So this would be the vertex, and the parabola is going to look like this. I'm graphing it lightly. The second piece is a line with the slope of 1/2 and a y-intercept of 1. So I find the y-intercept at 1, and I'm going to show lightly a line that has a half slope. So what I've graphed so far is each piece as if they're an entire own function. But these pieces are only defined for certain values of x. So now it's time to pay attention to when it's linear. Only for values that are greater than x am I going to have my function values on the line. I need to put an open dot here to represent the fact that I am not on the line at 2, but only for values greater than 2, which is this part of the line. I'm going to have values for f on the parabolic piece for values of x that are equal to 2, so I can make a closed dot at x equals 2 on the parabola and highlight all those values that represent values of the function for x values less than 2. And to be clear, in the final presentation of the graph, I ought to erase those parts of the graph that only guided me to complete the graph and bold the parts of the function that are meant to be a part of the graph of f. This is a graph of a piecewise function, and we say that it transitions from one piece to another at 2. So 2 is the transition, or a transition. A piecewise function can have many pieces, and it can have many transitions from one piece to another. It's important to note that this is a single function. It's not a function of two functions. It's just a single function. And this in this case, we must have more than one expression or piece for it to be piecewise. In this case, we have two. And the definition includes domain. And the domain must not overlap. Let's provide another example. I'm going to think of a cost function as a function of t, maybe for time. Think of something, maybe a rental of a tool. The first 8 hours costs a lower rate, but if you're going to use it for more time, it's going to become more expensive. We can model this as a piecewise function and consider the cost to be 12, maybe $12 for every t hour, but only in the first 8 hours when t is less than 8, or between 0 and 8. The function will not be defined for negative values of t. And then when t is 8 hours or more, we're going to use a different expression to calculate the cost. It'll be $96 plus $18 for every value of t over 8. So this expression is intended to capture the first 8 hours at 12, which is a $96, and then we add $18 an hour for every value of t in excess of 8. This is a piecewise function, and we can graph to model this cost. The cost goes up by $12 an hour until it reaches 8 hours at a total of $96. And then the slope goes up to model the fact that afterwards it's a greater rate, or greater constant growth of 18.